Okay, you're live.
Okay, great. So welcome to the second meeting of PNS Ramulator. Today we will start with some tutorial. So Hasan will explain us like in more detail about the design of Ramulator and how we can use it to perform like various memory system simulations. And in the second part, we will go over the projects that we offer in this course, and we will expect you to tell us your preferences. And yeah, afterwards we will assign you a project that you will be working during the rest of the semester. Okay, so like, let's see. So that is for later. I'm just like checking if there are like some other announcements that I want to mention. Okay, no, I guess the rest is for later. Okay, yeah, so we are starting with the Ramulator tutorial. So like, yeah, you can take it over, Hasan, when you're ready.
Okay, yeah, thanks, Hassan. So yep. In this meeting, we are going to talk about how Ramulator is designed and how to use and extend Ramulator. So first, let's go with some basic design principles of Ramulator. The core of Ramulator is built around the DRAM state machine, and as various DRAM standard documents like those from JDAC, the DDR series standards, has shown, in fact, the functionality of DRAM is indeed modeled by a state machine. And in commercial DRAMs, the handling of the commands and how the internal timings of the DRAM operation is operated, they are also handled by finite state machines. So here we present a simplified DRAM state machine at the bank level that covers the most common operations and state that a DRAM device can undergo. So first, the initial state would be in an idle state. And in this state, if the bank receives an activate command, it will go into the activating state. And after a certain time has passed, it will enter the active state, or in other words, one row is opened in the bank. And in the row opened active state, the DRAM can receive read or write commands and transit into the corresponding reading or writing state. And when the DRAM is in active state, it can also receive a pre-charge command to essentially close the bank and return to the idle state. And of course, when it's in idle state, if it receives a refresh command, it will enter the refreshing state and wait for TRFC and transit back to the idle state. So in order to model DRAM, basically Ramulator uses a generic and extensible way that allows users to define such state machines, and the controller and state machine logic in Ramulator handles all the state transitions and the timing constraints. Then let's talk about the responsibilities of the most important part, other than the DRAM state machine in Ramulator, which is the memory controller. So the first role of the memory controller is an interface between the processor and the DRAM device. In Ramulator, the memory controller queues the read and write requests that comes from the processor or the cache hierarchy, and it will translate these requests into actual DRAM commands. Let's say if the request is a load request, then essentially the memory controller must issue a read command for this request. Second, the memory controller needs to schedule the commands of the request while obeying the timing constraints as defined in the DRAM specification. So in order to schedule the request, the memory controller will choose the request according to the defined scheduling policy, and then it will issue the corresponding DRAM command that is required to complete serving the request according to the current state of the DRAM device. And while it's doing all this stuff, the timing constraints between these DRAM commands must not be violated. Third, it also performs various bookkeeping operations. For example, it will periodically issue refresh commands according to the defined refresh strategy of the DRAM standard. And in some cases, we build RowHammer protection at the memory controller level, and this is also handled here. And of course, if you extend Ramulator, it will probably perform more these kind of operations. Then let's step into the detailed design of Ramulator by following the life of a DRAM request. So first, a request is generated when the processor is ticked. It reads the processor trace file and parses the corresponding read and request from the trace and send it to the memory controller through the enqueue function of the controller. And then when the controller ticks, first it will serve any previously completed read request and cause the callback on the processor side to the request to basically fill the corresponding cache lines and continue and unblock the pipeline. Second, it will tick the refresh controller in order to perform refresh bookkeeping operations. For example, incrementing the refresh counter and actually issuing the refresh command. Third, it queries the request scheduler to find a best request to issue its corresponding DRAM commands. And once the command has been picked by the scheduler, Ramulator calls the issue command function with the command and the corresponding address vector as parameters to actually traverse the hierarchy of the DRAM finite state machine. So in order to do so, it basically performs 3 steps. So first, it updates the DRAM state machine in a recursive manner through the entire DRAM hierarchy. Let's say from the channel to the rank to the bank groups and up until to the banks. And this is done in the update state command method in the controller class, and we will get back to this very soon. Second, it will handle the timing constraints for the just issued DRAM commands, also recursively through the entire DRAM hierarchy. And this is done in the update timing method of the controller class. Finally, it updates the row table if necessary. The row table is a special data structure in Ramulator that is used to optimize the basically the DRAM hierarchy. In Ramulator, we only model the DRAM hierarchy recursively up until the bank level, because a bank contains too many rows that if we model every single row as a DRAM node in the hierarchy, the performance would be catastrophic. So instead, we use a table-like structure to track the individual states of each row in a bank. In the common implementations, we only keep the corresponding data of the currently activated row per bank in the row table. So first, let's get into the implementation details of the DRAM state machine by taking a look at how Ramulator updates the state of the DRAM device recursively. As we can see here, let me enable the laser pointer. Oops. Yeah, give me a. Yeah, is there a like a laser pointer in Zoom?
No, but there is on in PowerPoint, so you have to use that.
But I think it's usually on the bottom left of the slide. But
I think you can also enable it by right-clicking and then selecting it from there. No, I don't see.
Okay, so yeah, I think I will make sure by just drawing.
Yeah, so you can see your mouse actually. So
okay, is my mouse clear?
I think so, yeah.
Okay, cool. Yeah, so yeah. So when we update the DRAM state machine, the most important part here is we call the lambda function of the corresponding command at this level. So the lambda function basically defines how the state of the DRAM will change at a certain level according to the current state of the device. So let's take a look at the Ramulator code to get a better understanding. Okay, can you see the code? Benedict, yeah. Do I need to zoom in or is it good for you?
It is good.
Oh, okay, yeah, thanks. So here are the examples of how the lambda functions are defined. So first, the lambda variable is a two-dimensional array of lambda functions. So the first index indicate at which level in the DRAM hierarchy is the function applied to, and the second index corresponds to which DRAM command will trigger the state change, and the function body describes what the state changes actually is performed. So let's say when an activate command is issued at the bank level, this just changes the state of the DRAM bank to opened, and also updates the row table to indicate the row address accompanied with the activation command is opened. And vice versa, if a pre-charge command is issued, the code clears the row state and also closes the bank. And some more examples follows here. Because the DRAM device is organized in a hierarchical way, so we can access the child nodes of a DRAM device if the command needs. Let's say for the pre-charge all command, what it does is that it pre-charges all the banks in a rank. So what we do here in this lambda function for pre-charge or command at the rank level is that we basically iterate through all the bank groups of the rank, and for every bank group, and for every bank in every bank group, we basically close the bank and clear the row states. Yep. Is there any question about how the lambda functions are defined and how are they used? Okay, cool. Yes. So if you have any question, just feel free to interrupt and ask. Thanks. Okay, so let's get back to the slide. The second important part here is involves the scope as defined in the DRAM standard. So we terminate the recursion of the DRAM state machine if we have reached the scope of a DRAM command, or if we have reached the end of the hierarchy. So this is an important optimization to avoid traversing through the useless parts of the DRAM device. And the scope is basically just in 1D array, and it's indexed by the DRAM command that basically returns the scope of that command when you access it, or when you access the array indexed by the command. So let's say for the activate and precharge command, their scope is at the bank level, and for the just shown precharge all command, its scope is at the rank level. So this means that when we process a precharge all command, we can stop the recursion quite early, that we don't need to recursively check the bank groups and banks. Yeah. So the next part of the DRAM state machine in Ramulator is handling the timing constraints. So here we show the code that actually traverses the timing related part of the DRAM hierarchy and ensures all the timing constraints are obeyed. So here the update timing function is basically divided into two parts. So in the first part, we handle the case where the node we currently traverses is not a target node of the DRAM command and its corresponding address, or in other words, it's a sibling node. So for example, if you are activating bank 0, then all the other banks in the same bank group will be your sibling node. So there are some timing constraints defined in the standard that specifies the minimum time between two commands, two different nodes at the same level, and this is where the sibling timing constraints will take effect. So for the sibling case, the first most important structure here is a timing array. So this contains the actual timing constraints that is defined in the DRAM standard. So let's also take a look at the timing definitions. Okay. So here, this is the definition of a timing entry. So it has 4 member variables. First is the command that the timing constraint is constraining. The second is called dist, and we will get back to this very soon when we talk about the target node case. The third val is actually the value of the timing constraint in number of cycles, And finally, the sibling Boolean variable indicates whether this timing constraint is for the sibling node or not. And for the actual definition and for the actual instantiation of the timing constraint, we can take a look at the examples here. So still the timing array is a two-dimensional array, and the first index is also still the level in the DRAM hierarchy that the timing constraint is effective on, and the second index basically means that which the other command that the command indicated in the timing constraint is effective. So to illustrate this, let's go to the timing constraint that we are very familiar with at the bank level. So here, if you take a look at this line, so at the bank level, the timing constraint between an read command and the activate command is an RCD. And the timing constraint between the read command and activate command is also an RCD. Between pre-charge and read is RTP, and between activate and another pre-charge, it's an RP. And these are just like values that you will define for your speed entries. Let's say the as shown in the presets here. Okay, yeah, let's get back to the slides. So once we have once we find a valid timing constraint for the sibling case, yeah, because we are dealing with the sibling here, we calculate a future clock that's which is the earliest time that the same command can be issued again in the future at the current level. And this future value is compared with the value with the next value for the same command, and the maximum of the two is used to update the next value of the current command. And the next variable is an array that is defined for all the possible commands in the DRAM standard. Let's say if the current command is activate, then if we use activate to index into the next array, then the number we retrieve is the earliest time that another activate command can be safely issued without violating the timing constraint in the future at the current level. So another function called isReady in the memory controller and also used by the DRAM scheduler will check the next value for the corresponding command and compare it with the current clock cycle of the memory controller to decide whether it is possible to issue the command or not. So this is like the key timing logic in Ramulator. Okay, yeah. If it's clear, let's go to the second part of the update timing function. So in the second part, we deal with the case where the target node is, where the current node is the actual target node of the DRAM command and the address. So the update, update for the future array is like almost the same as the sibling case, but here we need to first deal with a case that's the dist member of the timing entry structure dictates. So if you remember from the JDEX standard for DDR3 and DDR4, you will recall that there's a certain timing constraint that involves more than one previous histories of the commands. Let's say the N4, the for activation window timing constraint basically says that no more than 4 activate commands can be issued within such a time window indicated by the value of the timing constraint. So in order to model this kind of timing constraints, for each command we have to maintain its history, and we put this as the prev array for each command, and each entry in the prev array is a vector whose size is the value of the dist member of the timing constraint. So let's say for all the common timing constraint that does not involve more than one previous commands, the dist value will be 1. And if it's the N4 timing constraint, the dist value will be 4. So basically, we are keeping 4. Basically, we are keeping like when does the previous 4 activate command is issued. So here in the logic indicated by the red box, we basically just maintain the history of 4 by popping the earliest history and pushing the latest history in. So once we have this, in order to incorporate this information, we basically add this part that takes the latest earliest history of the command and compared with the timing constraint. Okay, so next I will give a brief tutorial on how to use Ramulator. So we have been improving Ramulator internally, mainly to improve its usability and extensibility. So the presentation will be based on a preliminary version of this new Ramulator. In order to build Ramulator, we need the following 3 dependencies. We need the YAML CPP library to parse the configuration files and the FMT library to provide better string formatting. And we need a compiler that with C++17 support. And you don't actually need to do anything about the dependencies except for the compiler. The build system of Ramulator automatically handles the dependency for you. And for the compiler, I think if you are with a relatively new Linux distribution, you should have a GCC version that supports C++17. So you can get the latest Ramulator version through this GitLab repo. This repo should have the permission open for all RowHammer members. And please do remember to clone the repo recursively so that it also downloads the 2 libraries in the dependencies. Then as usual, you just like build Ramulator. So as mentioned before, Ramulator has all its configuration files organized in a YAML document. To run a simulation, you just simply run Ramulator with the command line option config followed by the path to the configuration file. Let's give a quick example. So yeah, if you just do this and it takes the contents as indicated by the configuration file and runs the simulation, and we will get back to the contents of the configuration file very soon. Ramulator also supports overriding some simulation parameters in the configuration file directly through the command line without the need to actually modifying the file on disk if you just want to change a small part of the configuration file. So let's say if you want to do some crazy experiment where you want to set the RCD latency to 50 clock cycles, you can just append the command line parameter, the command line option param, followed by the path to the NRCD timing constraint in the configuration file. So yeah, here the NRCD timing parameter is defined in memory.spec.speed, and you can override stuff here. So once we run it, we can see that the latency between the read command and the activation command is 50 clock cycles, while previously it's like 17. Yeah. Okay, let's get back to the slides. Oops. Yeah, and you can override multiple timing parameters by just appending this command line option multiple times. Okay, so but sometimes we want to perform large scale and more complicated parameter sweeps, or we want to do multi-program simulations by randomly picking 4 traces from our large pool of CPU traces. Then in this case, we would recommend to just use a Python script to automate and manage all the simulations. So it's also a very simple, just 2 steps. So first you parse the YAML configuration file, and the functionality is already implemented in the very popular PyYAML library. And then you added the parsed configuration, whatever as you want. Let's say you can loop through a range of values for some parameters, and then you just execute Ramulator executable through Python. So let's also take a look at an example here. So here, let's say, yeah, I want to see how the system performs when we increase the RCD latency. So yeah, we just import the PyYAML library, and with these 2 lines of code, we parse the YAML configuration file. But then we just modify the corresponding configuration as if we are just accessing a Python dictionary. And then we run the Ramulator executable with the freshly modified YAML document in memory without the need to write it back to the disk. So in order to support this, Ramulator also supports taking the entire dumped YAML document as a string as all the command line parameters, and the internal YAML parse of Ramulator does the parsing stuff for you. So if we run this experiment, yeah, and we can see that the NRCD values is changed 4 times, and yeah, so for the first iteration it's 20, the second iteration is 30, 40, and 50. So yeah, I think the automation with the parameter sweep with Python script is very straightforward and convenient. Okay, let's get back to the slide. Yep. So let's talk about the configuration file format. So in this new version of Ramulator, we completely overhauled the way that we input configurations to Ramulator. We use YAML as the format for both human and machine readability, as well as the ease of extension. So some quick background introduction to YAML. A YAML document is just a simple collection of hierarchical key value pairs, or in YAML terminology, nodes. A key is a string, or hierarchically, it can also be a node, while its corresponding value can be one of the following things. First, a scalar. It's the primitive types like integer, float, string, Boolean variable, things like that. Or a mapping, which is a collection, an unordered set of nodes, but without duplicate keys. Things like that is a mapping. And third, a sequence. So it's very like a list. It's ordered, but it can have duplicate keys because yeah, it's a list. Yep. At a high level, a Ramulator configuration file must at least contain a memory node that includes all parameters that describes the memory subsystem. If there's also a processor node in the configuration file, Ramulator will be driven by the CPU trace. Otherwise, if there's no processor node, Ramulator will run in the DRAM trace driven mode. So let's take a look at a Ramulator configuration file. So here is the configuration file that we used to run the previous short examples. Let's first take a look at the configuration format for memory. So in order to start a memory node, you just write memory here, and then you specify the DRAM standard you want to use, and then here comes the spec, which contains the organization of the DRAM. Let's say how many banks, how many bank groups, how many ranks, how many channels, things like that, and also the size of the columns, how many rows are there in the bank, the size of the DQ is, yeah, things like that. And if you specify the configurations for individual levels after the preset, it just overwrites the corresponding values in the preset. And usually we already have multiple DRAM organizations defined as presets that fits the most popular needs for DRAM devices in our implementation. The same goes for speed, which is basically the frequency of the memory and all the timing parameters. So you can also start with a preset as we already defined according to the JEDEC standard. And then you can also override some of them by just writing these overridden values below. So here, if a timing constraint is prefixed by t, then the value will be treated as in the unit of nanoseconds. If it's n, then it will be treated as in the number of cycles. Then you also specify in which refresh mode the DRAM operates. And after you have finished configuring the actual DRAM device, you specify how your memory controller is composed of. Let's say the address, how the physical to DRAM address mapping is done, what kind of scheduler you use, the parameter for the schedulers, the row policy, the parameters for the row policy, and what type of refresh you want to do. Yeah, and here are just like more parameters that can be useful when you want to debug your implementation. You can choose to print the command trace as we have done here, or you can like dump the command trace as a file if you want to debug larger traces. And also you can specify how the virtual to physical address translation is done in the memory system. Yep, let's get back to the slides. So next, I will briefly talk about how we can extend Ramulator. So first, I will introduce what are the key components that we have made abstraction of the whole workflow of the memory system. So first, we have the memory class. It's basically an abstraction of the memory subsystem that implements both the hardware and software interface between the processor and the DRAM controller and the OS and the DRAM controller. So the hardware part are those request queues that the processor uses to enqueue and receive the completed request from. And the software part is basically the virtual to physical address translation. And second, for the DRAM controller, other than the basic operating logic that we have demonstrated in previous slides in the life of a DRAM request part, it contains the following 5 key components that you can freely extend and modify. So first is the address mapper. Basically, it maps the linear physical address in the DRAM request to the actual DRAM address that points the DRAM commands to the bank, to the rows, to the ranks of the DRAM device. Then we have this the request scheduler. Its responsibility is to pick the best DRAM request to schedule according to the current state of the DRAM device. For example, our most familiar FCFS, first ready, first come, first served, request scheduling policy is implemented here, and basically it checks the all the requests in the corresponding request queue, and for each of the corresponding command, it checks whether the command is ready and picks the first ready command to serve. The third component is the refresh control. It generates the refresh commands according to the refresh policy. And fourth is the row policy. So it basically manages how the memory controller will close a row after it has been activated. So we have already implemented various policies like close page policy, open policy, or timeout open policies, and you can pick this in the configuration file, or you can extend the class to add more. And finally is the row tables that we use to keep track of individual rows for every bank. The third important high-level class is the DRAM class. So an object of an instance of the DRAM class represents a node in the DRAM hierarchy, and the methods we already implemented in the DRAM class actually implements how we traverse the hierarchy and update the corresponding state and timing information. and this traversal is initiated in the issue command function of the DRAM controller. So if your work involves, let's say, querying the state of some DRAM node, let's say a bank, if you want to see, let's say if you want to implement tiered latency DRAM, you want to know whether your current command is issued to a near region or a far region, you can just modify the logic in issue command and checks the address vector, and then modify your command to a low latency version or high latency version according to your address. The fourth component is all the definitions for the DRAM standard like DDR4 and DDR5. And as we have shown previously, we specify the organization, the timing constraint, the lambda functions that triggers the state transitions, etc. So if you want to implement some designs, these classes are the first that you want to investigate and extend. So for the memory and all the memory controller components, we all implement abstract base classes as the standard interface to communicate between the standard memory subsystem logic and the memory controller logic. So in most cases, you should just need to inherit from the base class and write your logic there. So here we present some general rules that you can refer to when you're extending Ramulator. So first, you should think about how to make your design and its implementation modular. So you first think about in which part of the design does my logic belong to? Is it like a new scheduler? Is it let's say a RowHammer defense that fits in the refresh logic? Things like that. And the second question is whether your design is very specific to a certain DRAM standard, or is it like a general technique that can be applied to many DRAM standards? Then after you have think about that, you can start to implement your design by inheriting from the base class that it fits. And if the difference is small compared to the existing common implementation, so you can just inherit from the common memory controller implementation and just override the single function that is that contains your logic. Let's say, as the previously described TLDRAM example, you should just need to modify the issue command function. Or if your design is specific to a certain DRAM standard, or in other words, if certain DRAM standards need some workaround for your design, then you should try to implement this as a specialization to the existing templated common implementation, other than trying to present it as a new class. Finally, you add your new design to the factory methods of the corresponding base class. Let's say you implemented, you inherit from the base class for the scheduler that you implemented your customized scheduling logic. So you just go to the make scheduler function and add very simply several lines of code to let Ramulator recognize and instantiate your new scheduler when it encounters that configuration in the YAML file. And we can take a quick look at that. So here's the definition of the function that instantiate different variants of the scheduler. Let's say if you have a new scheduler, you just, let's say, copy this and change this to your, as a new scheduler, and boom, then Ramulator will be able to recognize and instantiate your new scheduler when you type new scheduler as the type of the as in the scheduler configuration. Okay. And in order to add a new DRAM standard, you basically start with copying an existing DRAM standard to reuse the definition for all the necessary data members of the class that is expected by the common memory memory subsystem and the memory controller logic. Then you add new levels of the DRAM organizations to your new definition, if there's any. Then you add the new DRAM commands introduced by the new DRAM standard, and what are the corresponding functions that is needed by these new commands to update or query the DRAM state machine. And finally, you add the new timing parameters introduced by the new DRAM standard and the corresponding timing constraint between DRAM commands at each level in the DRAM hierarchy. And last, you implement any specialization that might be necessary to the new DRAM standard in the memory controller components. Let's say if you want to implement DDR5, then the per bank refresh is unique to DDR5, so you need a specialization for the refresh logic only for DDR5. So a tip here is that if the difference is very small, instead of writing an entire specialization to some very lengthy functions, you can try this sweet C++ 17 feature called conditional compilation with if constant expressions and type traits to basically enable and disable part of the code at compile time. So for a more detailed walkthrough of how you can add the DDR5 standard based on the existing implementation in Ramulator for DDR4 and the common memory controller logic, you can take a look at the README of the Ramulator repo. Yep, and that's all for my Ramulator tutorial. And if you have any question, please feel free to ask.
Okay, I guess everything is clear. Thanks a lot, Hassan.
Yeah, but I think Benedict's microphone icon is like enabled for a bit, but I don't see any activity. So is there any question, or is your microphone like maybe broken? Okay, I think yeah, if like your microphone is problematic, you can just type in the chat, Benedict, because we can't hear you and your microphone is like unmuted for a while. Ah, okay, cool. Yeah, cool.
Okay, great then. Yeah, thanks again, Hassan. And we can continue with the rest, right? Which is like we'll start looking at the projects that we offer this semester. So this will happen off record.